Hey guys, so today's tutorial is basically going to be just about setting up an n-body simulation in Excel. Um, Not only that, but we're also going to look at a few little tips and tricks in Excel to do some cool things, like set up this viewport, which is actually just a simple chart in Excel, but can be quite tricky to set up something like this if you don't know exactly where to start. So I'll be going through that as well. And just in general, just one thing that I hope speaks out from this video is just if you lay out things in a particular ways in Excel, it actually makes reading the spreadsheet very simple, and understanding what is going on in the spreadsheets makes that whole process a lot easier. So when you show your spreadsheet to someone else, they look at it for the first time, they think, oh, okay, cool, that's something I can get behind, that's something I can understand. Whereas, if it's just a pile of columns without any headings, it's a lot more difficult to understand what's going on. So just, I'm not going to go into that in particular. I might leave that for another video. But just in general, just the style of how I set things out hopefully looks quite visually appealing. But yeah, basically what this video consists of is how I've set up these equations, or the equations that sit behind these calculations. How I've actually set those up in Excel, and that's goes through the various tabs. I don't look at any of the VBA code, although there is very little. But what I do is just give a sense of, okay, cool. If you've got something like this that you want to set up, this is how you go about doing it in Excel, to give you a very visual feel for the problem at hand. So if you press start over here, that actually does nothing, but then you just have to press the right arrow key, and what happens is the n-body simulation occurs. So one time step occurs, and it all depends on what your time step is. Got a time step over here, but I'll be going through that now. But let's just go and press. So every time you press the right arrow key, it updates the kind of the visual screen over here, and you can kind of see these asteroids or whatever kind of flying past the planets in the middle, and that all looks pretty cool. So I'm going to be going through how I set up the spreadsheet, how I set up the calculations, where I got all that information from, and then some little tricks, as I mentioned, on Excel that lets you set up a visual tool like this. And yeah, so let's see how I did all of that. Right, so the first thing that I did to be able to create the simulation was all I did was I just looked at on Wikipedia. It's not rocket science. But basically, yeah, I mean, just look at Wikipedia for whatever you want and just try put that into Excel in the various formulas that you can get. That's I'm not going to pretend that I fully understand all of this stuff. I definitely don't, and it's possible that I might have slightly got the calculations wrong. If I did, please let me know. I'd love to be able to. Do them correctly. So don't assume that everything I've done here is perfect. But it's a good first stab, so to speak. And so this Wikipedia tells you basically everything you need to know. So it's pretty cool. Unfortunately, I guess you just need to kind of figure out what it is that you're actually looking for. So in this case, gravitational constant seemed to have, or the article on gravitational constant seemed to have all the stuff I wanted. Maybe it's in some of the other articles of similar nature, maybe not, who knows. For instance, if you look at orbital mechanics, I think some of the equations are there, but not all of them. Or you'd have to click on other articles to find the other equations. I mean, basically the only equations we really care about, at least in this spreadsheet that we're talking about, is just this equation, which basically looks at two objects that you care about, which is the mass of the two objects, object 1 and object 2, the distance between those objects, r squared, this kind of constant number, which is actually this gravitational constant, and multiplying and dividing all of those together gives you the force that acts on one body, um, um, or acts on two different bodies in relation to one another. So basically, body one would be affected by that force, and body two would also be affected by that force, but in opposite directions. And basically, all that means is, okay, cool. In Excel, what would you do in Excel, right? You would set up one column maybe that has like this number. Maybe if you've got another column that has this number, you've got another column that has this number, and one that calculates the distances, which we can do. So you need the location of the two objects, and then you can calculate this guy. So that's pretty easy, and we'll see what I've done in the spreadsheet. Hopefully I've done that fully correctly, but let me know if not. And then, we look down here, orbital mechanics. Cool. So there's different kinds of G's you can use, and depending on what these R's and M's are relating to, the G can basically be different numbers. So, if you just use like kind of, what is it, kilograms and meters, then I think, where is it? Then you need to use like the normal G number that you would learn in kind of science at high school. So it's kind of it's 10 to the minus something, big number. I'm not sure if it's exactly this one. It looks like it's probably this one. But yeah, there's kilograms, there's there's meters. It's probably this one. Oh, it's this one. Here we go. So it's 10 to the minus 11. So I was like, I don't really want to use 10 to the minus 11. I want to find something that's closer to like, 10 to the 0 or 10 to the 1 or whatever. So this one seemed pretty cool. So in astrophysics, convenience to use these numbers. So it's like, cool, I'll just use this one and pretend that all my, masses are in whatever, solar units. So I guess, solar units, we could look at exactly what that is on Wikipedia. And kilometers per second instead of meters per second. That's quite nice. You're getting a kind of higher level view of how maybe a kind of a galaxy would work, or a solar system, as opposed to kind of just like very small objects having very limited impact on one another. We can just pretend the things that we're looking at are very large objects like planets or suns or stars, I should say, or whatever it is. Right, so this is the first page on the first sheet on the Excel workbook. Basically, we'll come back to this one because it's more interesting once we've actually looked at the rest of the spreadsheet. But basically, it just allows you to set up initial values for the engine. But we'll worry about that a little bit later. Here's the engine, and what this does, as I showed you at the beginning of the video, if you just press start, it updates the simulation every time step. And that's pretty cool because, that basically allows you to do an M-body simulation. Now, what we've done here is we've actually got 100 objects. So that's not too bad. I mean, in C++, you could probably get about 2,000 objects before the simulation starts screeching to a halt. But, you got 100 objects, and it works pretty nicely in Excel. I mean, there's no significant delay from you pressing, to forward the time step by pressing the right arrow key as I've set it up, to, seeing the results happen in front of you. So obviously it's not going to reach the speeds of a programming language, but for what this is, very visual way of seeing, your calculations, that's not too bad. It's not too bad. So anyway, what are the things we care about? So I might have laid this out in a slightly strange fashion. And I don't have the X over here. I'll explain that in a second. I'm just going to rewrite it in. But we are going to take it out in a bit, just so I can show you a little trick in Excel. But I put it back in there. So what do we have here? We've got the velocity of each object in the X direction. So X is horizontal. And the velocity components in the Y direction. So Y is vertical. And the same thing, we have the X and Y location for each of these objects. So as you can see, this first object this first object, I'll always set it up, and we'll see that in this tab later on. I always set it up to be an incredibly massive object that sits basically at the center of the simulation. So the world coordinates are very close to 0, 0, which is the center of the graph. You can see this guy is a little bit to the kind of left of the center of the graph and down from the center of the graph. And that's exactly what this is saying. X coordinates, it's negative values are to the left, and negative Y coordinates are down. So you can see this guy is kind of diagonally to the kind of bottom left in this direction, which is exactly what this is saying. And then this is saying, okay, he's moving slightly down and not so much in any horizontal. So he's kind of moving in that direction, and he's sitting slightly to kind of from the origin, sitting slightly to the bottom left of the middle of the graph. So when I say origin, I mean the exact center of this graph. So we got the velocities and locations, and you can see that for every single object. You can see the radius and the mass. So the radius is simply one way that we can do to determine the different sizes of our objects. As I mentioned, I've made the first object to be the largest object, which also has a large radius. So large in terms of mass, in terms of density, so to speak, and in radius, just in sheer size. And then what we can do is we can calculate, based off of this information, looking at all 100 of these guys, we can work out what is the total acceleration that any of these objects are going in either the kind of the vertical direction or the horizontal direction. So the Y or the X, or should I say X or Y, right? Horizontal, vertical. These accelerations will then impact what velocity you have, and this is just, you know, Newton's laws, or what is it, laws of equations of motion, right? So that's another thing we could look at on Wikipedia. I'm not going to go there, but that's something that equations of motion, Newton, have a look. But that's basically exactly what these are. So if you remember from high school science, basically your acceleration is the mass, and we'll come to this formula is basically saying it's the mass, it's the force being applied to the object divided by the mass of that object. So if you have a larger force, then you have a high acceleration. If you have a larger mass, you actually have a lower acceleration because it's more difficult to move you because you're so massive. That kind of makes sense. And then the velocity and locations in the next time step that we care about are just going to be whatever your velocity is now, adjusted by acceleration. And the location allows for, it's one of those laws, again, one of those equations of motion. So it looks at the new velocity, the old velocity, and kind of finds the average of those and adds that onto the location. But all these calculations, if you can see, this force X, force Y, so those actually are applied from these tabs. And we'll come on to these tabs in a second. So these tabs require the calculations from these to work them out. And all these are, it's just those, it's just that from that Wikipedia article, it's just those calculations broken out into big tables, because every single object, let's remember, every single object is going to have some force being applied to it from every other object. So you have to do kind of a massive set of calculations for every additional object in the simulation, because every new object you add in will impact every single other object. So you need a whole bunch of new calculations for every object you add in. So if you've got 100 objects, you need 100 times 100 calculations, which is exactly what this is. 100 times 100, and it's just 101 because I've included the column and header row headers. But so basically we've got 100 by 100 calculations here. And what are these? Okay, so if you remember in this formula that we had R squared at the bottom, which is distance between the bodies squared. So all I've done is work those out. Now these offsets are really good in Excel. They look a little bit strange. But basically all it's saying is you start at cell B7 in the engine tab, and then I want to move from B7 by some set of rows and some set of columns. So if I've got all my object names or numbers at the top and to the left of this big table I'm setting up, I can just offset by these numbers and find the relevant information I want from these guys. So where I was starting in those offsets is B7, and say, okay, cool. I just need to go down by the amount of rows that this number represents, say 30. And for this one, I just need to go down by the number of rows of 17. And then I'll be able to get all the information I need from the two objects that I care about in this particular case. So I care about object 30 and care about object 17. So what do I need for the distance between the bodies squared? Well, all this is saying is that I need some information about their locations. And then I do some kind of minimum calculation. If that distance is below some number, then I kind of ignore it, because otherwise you get infinite force, and that's not a good time. No one wants that. So what we do is we say, okay, cool. Let's go down by 17 rows and find the two location numbers that I care about. So that would be, I need to move 1, 2, 3, and 1, 2, 3, 4 for columns, or 3 columns, to get the relevant location information for number 17, and the same deal for number 30. That's all that these guys do. If we just look over here, it's just moving down by 30. It's moving down by 30, and it's moving to the side by 3 or by 4. And that just gives you the locations they would care about. And to find the distance between 2 points squared, it's just x, the x location of one object minus the x location of another object. So it's these two numbers. You minus 1 from the other and square the result. You do the same thing with the y components, times them, minus them from each other, and then square that result. And then you add those two values together, and that's your distance squared. So boom, that's exactly what this calculation does. And unfortunately, we actually, what I've done here is I've just replicated the formula for, okay, that's actually the formula I want if it's bigger than this number, otherwise I want 0. It might be a quick way to do it in Excel, but whatever, that gets you the result you want. Cool, so now we've got the r squared value, and if we just have a look over here, we got the r squared value. Cool. So now we have the r squared value in this formula. But now we need our forces. So what we're going to do is find the force, the magnitude of the force that we care about, and that is called. And then we're also going to find the direction of that force. So for each body in our calculation, say these two bodies over here. We've got this guy is being attracted to this body in this direction, and this guy is being attracted to this body in this direction. So we've got to make sure the force that we're being applying to each of these objects have the right direction. So, or the right direction in x and y, in the x and y components. That's how I've broken it out here. And then the magnitude also needs to be allowed for the force. Now, once we have the magnitude for the force, we just divide. This is what this guy does. Just divides that magnitude by the mass of the object we're looking at. So, okay, well, if I'm an absolutely massive object, well, that force is going to have very little impact on me. If I'm a tiny object, it's going to have a huge impact on me. Which kind of makes sense. So that is all that we do on this tab, is we just look at the, so we got our r squared calculation here. This is our gets our two masses, and this is our gravitational constant. So this is that formula that we saw on Wikipedia. There's nothing more than that. You just have to do it for every single object. Now, it's probably a bit of double counting, or there is double counting in this calculation because we don't need half of this half of the square, right? We can get rid of the top right-hand side of this massive triangle here because these numbers are symmetrically exactly the same. But I've set it up in this way that, we actually do those calculations, a bit of a waste, but we do those calculations just because it makes the calculations on these tabs a lot simpler to look at. But if you really wanted to save on calculations, you could and should get rid of this top right-hand side of the table. Okay, so what we do here now is we just break out this force, or we just break out that force into its x and y components. So it's just a simple formula that looks at, depending on the difference in the x locations of the two objects and the y locations of the two objects. Say this guy and this guy, the two x locations are there, and the two y locations, the distance there. So most of the force should be in a kind of upwards direction for this body, and some should be in the kind of the horizontal direction, or to the right. And that's all that these formula do. Now it's quite interesting to see that for this guy and this guy, these are symmetrical, right? This is the force that acts on object 3 from object 1, and this is the force that acts on object 1 from object 3. I think I said that the right way around. But as I mentioned earlier, and this makes total sense, that force should be in the opposite direction, because one is applying from one object. If we just look here, one object is moving in that direction, but this object should be moving in this direction. Now this object will move only a very little bit in this direction, because it's going to be divided by a massive mass. This object should move a lot in this direction because it has a very little mass, and the force will be quite big. That same force will be, most of it will be applied. So that is all that's actually taken. We just take those various forces and we add them all up. So, and that's what this column, this row does over here. Just adds up all of the various forces that act on body 1. And it adds up all the forces that act on body 2, etc., etc. And that gives you these sets of numbers. So all we need to do is just find this object over here, and then take that number out and put it in here. So that 1.1 eta minus 3, I think that's that's this one, 1.1 eta minus 3. That looks correct. Etc. etc. The force, the y component of the forces are here. It's the same thing. Now we have all our information to do our calculations, our equations of motion, because we have acceleration now, so we can find the new velocities and new locations. So all we need to say, okay, cool, we have the current velocity and locations. These are the new velocities and locations. So all we need to do is actually just copy these values and paste them over here. Now all of these have been updated, all the locations have been updated, all the velocities have been updated. That means, well, especially because the locations have been updated, that will give you different radius or different distances between those objects, therefore different gravity forces between those objects. And that will update all of these gravity forces or accelerations, which give you a whole set of new numbers, which you can then copy paste over here to give you your new values for the next time step, etc., etc., etc. That is all we do when we press the start button. All it does, I'm just going to press to the right, and all it's doing, you can see it's kind of highlighted this area because it's copied the values here onto here. And I'm just going to press right a few times, and you can see it's taking the values. Let's see this, minus 83.6, and if I press right, there we go, it's now changed to minus 83.6. I can just press right. What I'm going to do, I'm going to fast forward now, just so you can see what it looks like after I press right, like a few, I don't know, quite a lot of times. Let's have a look. Right, so there you have a nice little simulation. Definitely got some kind of repetitive strain injury there, but that was quite fun. That looked quite nice. Um, now the problem is that all our objects have actually kind of moved off of the screen here, which isn't very helpful. So what we're going to do is we're going to look at this tab that I mentioned. Here you can see the initial object is set up with a pretty large mass at the origin or at the center of the screen. And then these are all just random numbers that I've generated using just some starting values. What these starting values allow you to do, and I'm not going to go through them, but it just allows you to set up kind of random locations. And depending on those random locations, it gives you a velocity that just makes sure that the objects that when they're initially set up go in a kind of circular or anti-clockwise direction. If you don't do that and you all set the velocities down to 0, all the forces, and let's just copy paste these guys in there. We can actually, why don't we look at what happens? Let's set all the velocities at the beginning to 0 and see what happens if we run the simulation with all the initial velocities set to 0 rather than what I've done for the velocities over here. We'll press start, we'll move. And then clearly what's going to happen is all the objects are going to float or be attracted to the center of the of mass. And because they don't have any other initial velocity, you just have this problem where everything just gets sucked into the middle. And to be honest, it's a bit of a boring simulation. I mean, it can look quite cool in some instances. I'm not a huge fan. It does have, it can be pretty cool when you've got like, I don't know, maybe 1 million objects, or I've been able to get up to 250,000. You get this kind of cool, I don't know, like vortexy. It's not a vortex really. It's just kind of a black hole kind of situation. It looks kind of cool, I guess. But I would suggest to play around with different types of starting setups. That look a little bit cooler than that. So we'll end that simulation. Let's go over here and let's copy paste these guys again into here. But now they have these different starting velocities, and those velocities, like I mentioned, just give them a bit of a circular kick or anti-clockwise kick here. So it looks a little bit more like what you'd expect from a solar system or galaxy or whatever. So that's why they all move in that direction when they start. Okay, so one thing that I haven't spoken about, which I think is quite interesting, is actually how to set up this screen or this kind of viewport that we've been using. It's very simple, but it's one of those things that if you don't know how to do it, it's highly annoying to actually figure it out. So what I'm going to do is explain that now. And hopefully that you can use this in so many different situations. I've used this kind of thing for drawing maps. I've got a map of the UK that I've drawn using all postcodes, and you can kind of set it up. It's because it's an XY coordinate system. If you just instead of X and Y, you have latitude and longitude, or whichever way latitude and longitude are. You can set up a map if you've got your lat longs for your various positions in the UK or whatever it is. You'd have some kind of massive spreadsheets and you do this chart. It looks pretty cool. But what we're going to focus on is these guys. Now, how do you create it? If you go and you can do like scatter plots, I guess. Problem with scatter plots, I don't think there's a way that you can get different sizes of your objects. So you get this kind of thing where you've got all the objects in the kind of right locations, but you don't have different sizes, and we want different sizes. So what we're going to use here is a bubble chart. And what you want for the bubble chart, you want your X or your horizontal locations first. You want your vertical locations second in your second column of data. And then you want the size of each object in your third column of data. And fortunately, we've set up our data in exactly the way that we want to represent it in this graph. I happened to do that because I knew what I wanted. Sometimes you have to switch your columns around to get them in a format like this, or you can go and select data. I'm sure there's a way to do that using select data. I'm not going to show you that way because it's just fiddly and annoying. What we're going to do is look at how to set it up just when you've got your 3 columns sitting next to each other. So what I do is I put in my X coordinates here, put in my Y coordinates here. I've got my size of bubble coordinate values over here. And then here's a little trick that I've learned to do with charts in Excel. What you want to do is you want to delete this value, this heading of your first column, right? So when you select all the thing at the top left here doesn't have any values, completely empty. And that just always makes sure that the chart that you create just works. I don't know, it's one of those things in Excel, if there is a heading here, then it thinks there's particular values that it wants to generate from here. It all becomes incredibly annoying. It doesn't give you what you want. What you want to do is get rid of the value over here and highlight the 3 columns. And that works for, like, if you're doing line charts or any of those kinds of charts, there's always that issue. And to be honest, I have no idea why that issue is there. It's because this should be like 1s, 2, 3, 4, 5, 6, whatever. It's just an annoying thing with Excel, but once you know the trick, just get rid of the value over there and everything kind of works for you. You don't have to go and select data or do all this other stuff. You can just set up the chart very quickly from the data you have. Just got to get rid of that little, that little heading over there. Right, so now what we're going to do is we're going to go into Babble. And as you can see, it's already looking exactly in the way that we want it in general terms, but it's a little bit messy. I like this approach. Some people might like all these grid lines and whatever. I like having it so that I don't have grid lines. I've just got a very clean chart. So what I do for these kinds of things, I'll get rid of the chart title. I'll get rid of all my grid lines. But before I get rid of the grid lines, I do want to do one thing. I just want to format these axes. And what I've done here, this is pretty important. Doesn't really matter what these values are. You can scale it to whatever you want. But typically speaking, for this kind of thing, where we've got the center, the origin, we want to be right in the center of the chart. We want to make sure these values are the same values, just one is a negative and one's a positive. That makes sure the distance from the middle to the left and the right-hand side, in this case, left and right-hand side, is the same distance. And we want to make sure the same thing for the y-axis, which they are, so that's good. And these things, hopefully they're fixed and they're not automatic so they don't change. That's something that you'll want to make sure as well. But certainly what I then do, once I've got that correct, I'm going to get rid of these axes. It just cleans everything up and it makes it look quite nice. Now this one's a bit more zoomed in. I think I've got them at -1,000 to +1,000, whereas this one, as we saw, was -1,500 to a positive value of the same amount. So, it's a bit zoomed out, so to speak. Another thing, clearly these bubble sizes are a lot smaller. I quite like the transparency in this one. I might keep it and get rid of this chart altogether. But for now, I'll just show you what you need to do here. Format data, typically speaking, what I'd like to do is I like to go to width, and then this number for sure needs to be quite a bit low. So you've got to play around with it. Let's put it to 50. And then, as you can see, these are looking a lot more. So I think this one's set at 50 for width instead of area for these guys. So you go to format data, what is the format data series, and then you just choose your size represents width of bubbles 50. And what it's doing is it's basically setting it, depending on what the radius is, it's setting your bubbles to that size. That's exactly what we want. If the planet's got a bigger radius, or the star has a bigger radius, you want it to look bigger on your chart. Perfect. Okay, so now we've got our X coordinate, Y coordinate set up with the origin in the middle. Our bubbles, we can turn on and off transparency. I'm not going to go through that too much, but it's somewhere in here. One of these guys. I quite like that transparency, actually, kind of see what's going on behind the various objects. I don't have collision detection on here, so you can get objects flying behind other objects, that kind of thing. But one thing for sure that you'll want to do is you want to make sure that your charts, height and width, are the exact same number. So these two are very similar numbers. So this looks quite square, but sometimes you might have your width is 10, and then the problem here is that this represents 3,000 from negative 1,500 to positive 1,500, 3,000 units going across. But this is also 3,000 units going from top to bottom. So everything's going to look compact horizontally, and we don't want that. So we want this thing to be square. So I'll set it at 20 and 20, and now we've got a nice square exhibit chart, and that just, it shows the coordinates in the kind of, what we would expect, right? You would expect if that's 0, 0, you want that to be kind of, 1,000, 1,000 in kind of, in exactly diagonal. You don't want 1,000, 1,000 to be like up here. That doesn't make any sense. It's got to be like it's got to be exactly diagonal from the starting origin or middle location. And that is how you set up a bubble chart for these kinds of things. I think it's pretty cool. The big thing to remember, just get rid of this value. If you set it up with that X in there and you go highlight these guys and then insert your bubble charts, almost guaranteed that you're going to get some weird results, and then you've got to go fiddle around with removing data or whatever it is. So once you've got your head around these various calculations, the cool thing is that all you need to do now from a programming point of view, or from a simulation point of view, is just each of these columns, just throw them into different variables in a programming language, and you've got your embodied simulation. Now, the problem is that once you go beyond a certain number of objects here, the thing's just going to get so massive that any programming language is going to get crushed, unless you're using the GPU. But even then, there's going to be some cap on how many objects you can simulate at once, because just the number of calculations just increase by the square of the number of objects you throw into the simulation. So what you then need to start doing are things like tree algorithms. I don't really fully understand those. I've just been starting to learn them myself. But once I've fully wrapped my head around a version of a tree algorithm, I am hoping to actually show that in Excel, which could be quite interesting. So if something like that interests you, or any other kind of spreadsheets in Excel, simulations, generating simulations in Excel, let me know in the comments below, and hopefully I can throw that into Excel and create hopefully what might be another interesting simulation in our favorite piece of software. Well, thanks very much for watching, guys. And as I mentioned, if you've got any questions or comments or ways that other things that we could do in Excel, just drop me a comment. And yeah, hopefully I can have a look at that then. Until then, take care, guys.